Don't make me rich. That's a joke. Mr. Dion will not monetize. Okay, so let's see here. Chemistry 3111. We're into the big chapters now. This is chapter 18, aromatic substitution reactions. And when we're talking about reactions, we're talking about a lot of reactions. And let me show you how many I mean. If we go all the way to the end of the class, okay, somewhere down here, oops, you can see that we're going to learn a holy host of new reactions here. Bromination of an aromatic ring, chlorination, nitration, sulfonation, alkylation, acylation. And then we learned some other reactions, some reduction reactions, oxidation, yeah, a whole bunch of different reactions here. And then after that, we're still not done. We learned nucleophilic aromatic substitution. This is called an SNAR reaction. So SNAR, we learned that. And then we learned elimination addition. So all the stuff that's on this slide and all the stuff that's on these two slides, or on this slide here, that would kind of be, somebody says, oh goody, okay? These are all the reactions that we cover. Somebody put a great one in the comment, another reaction wheel. That's what I call it, right? I call it the wheel of reactions. And you're like, well, wasn't the wheel some kind of medieval torture or something? Anyhow, that's not very uplifting, is it? All right. Well, one of the cool things about this chapter is you're going to see that a lot of the concepts in terms of mechanisms show up over and over and over. And so as long as you understand kind of the basics of the mechanisms, you can get through quite a few of them. All right. So let's just do a little introduction today to electrophilic aromatic substitution. This is the vast majority of the chapter. Okay. Most of the chapter involves electrophilic aromatic substitution. And we have seen that pi bonds in an aromatic compound are less reactive than those in a typical alkene, right? This is something that we just saw today at the beginning of lecture when we were looking at chapter 17. If you take cyclohexene, that reacts with bromine, no problem. But if you try the same thing with benzene, doesn't work, it doesn't react. But what we're going to see is if you take a benzene ring, okay, which is highly unreactive, but if you put it in the presence of a strong enough electrophile, something that is just a crazy strong electrophile, it's going to react, okay? So the idea is we've got to put it in the presence of a very strong electrophile, and then the aromatic ring is going to behave as a nucleophile. It's not the best curved arrow going there. But anyhow, and that's what we're going to see in the first section on electrophilic aromatic substitution. So check this out. If you take an aromatic ring like benzene and put it in the presence of bromine and you put iron in the reaction, all of a sudden it works. You brominate the aromatic ring. So we call this a substitution. Why? Because you're substituting this hydrogen for a bromine. So we call it electrophilic because the bromine is part of the electrophile. And then it's aromatic substitution because you're substituting a hydrogen on the aromatic ring for a bromine atom. And if you're thinking, well, what is actually the electrophile in here? Well, we're going to get into that in a little bit because there's a reaction that's occurring between the bromine and the iron that renders the bromine extremely electrophilic. So let's move on from there. But before we do, let's get a little preview of what we're going to see. Is we're going to see if we put an aromatic ring in the presence of a strong enough electrophile, it can act as a nucleophile, and we can do bromination reactions, chlorination, nitration, sulfonation. This group is called a sulfonic acid. Alkylation, right, to install an alkyl group. And the last one is acylation, to install an acyl group. So this would be alkyl, and this would be acyl. So we are going to see all these different situations where the aromatic ring reacts as a nucleophile, and we can put all these different substituents on. So without further ado, let's get back to that halogenation. It says, in the bromination of an alkene, the bromine functions as an electrophile. These little things here, this is supposed to be delta plus and delta minus. Okay, and we looked at the mechanism of halogenation and how we form a bromonium ion, and I'm not going to go into all the details on that, but you end up forming the bromonium ion like this. There we go. And then the bromide can come in and attack as a nucleophile from the opposite face, et cetera, et cetera. That is covered in chapter 8. Okay, it even says here chapter 8.9. So how do we do this electrophilic aromatic substitution? What happens is when we combine our iron into the reaction, the iron acts as a Lewis acid, okay, a Lewis acid catalyst. And you might remember that a Lewis acid is an electron acceptor, okay, so it accepts electrons to make the bromine more electrophilic, and it makes the bromine electrophilic enough to be attacked by the pi electrons in the aromatic ring. So again, the whole idea here is to put the aromatic ring in the presence of a very, very powerful electrophiles. Oops. So let's take a look here. So here's the reaction, right? We have our bromine molecule. This is our Br2, right? And it's reacting with our iron tribromide, okay, which acts as a Lewis acid. And if you're wondering where the hell did this come from, I didn't really say where it came from. It comes from a reaction between, if you react bromine in the presence of iron, you end up making iron 3 bromide. Anyhow, so that's where the FeBr3 came from. Anyhow, so the FeBr3 acts as a Lewis acid. We make this kind of complex here. And then we end up with a bromine with a positive charge on it. So this is a very, very powerful electrophile. Sometimes the book is going to draw this as your electrophile. And then if you just want to write a bromine with a positive charge, I would accept that in a mechanism. I would take no exception to that whatsoever. So let's take a look here. Here's the mechanism of the bromination of benzene. I'm going to put one of my stars on here because you do need to know this reaction, the bromination reaction. So let's take a look here. Step number 1, we get a nucleophilic attack from the pi electrons on our aromatic ring onto the bromine, the most electrophilic bromine in our bromine iron 3 bromide complex. Okay, and then we have an aromatic, well, we destroyed the aromaticity of the aromatic ring, didn't we? Right? It's not aromatic anymore because this carbon is sp3 hybridized. So we've gone from an aromatic ring to a non-aromatic ring, and it's got a positive charge, and we call this the sigma complex. Okay, you're going to see the sigma complex about 10 zillion times in this chapter, and you can see that the sigma complex has a bunch of resonance contributors here, and then in the last step we get a proton transfer between what's left over from our nucleophilic attack to restore aromaticity. So we go back to our aromatic ring and we make HBr and we reproduce or replenish our FeBr3. So we keep making the iron 3 bromide over and over, and that's the catalyst for our reaction. So if we compare addition on an aromatic ring versus substitution, you can see that when we do the substitution, we get an exergonic reaction. Okay, it's exergonic. Why? Because you end up with an aromatic ring in the end. Whereas if you were to do the addition reaction, it would be a delta G as being positive, right? It would be an endergonic reaction. And so we want a reaction where delta G is going to be negative, right? So substitution is actually preferred to addition because we maintain our aromatic ring. And that's why we cover aromaticity in chapter 17. That's why we go over it in detail in that chapter. So you can also use other Lewis acids besides iron 3 bromide. You can use iron 3 bromide, sure, that will work, or you can replace it with aluminum tribromide as your Lewis acid. That works perfectly well. And the good news is that the mechanism would be the exact same as written with FeBr3. There's no differentiation there whatsoever. And you can even use aluminum trichloride as a Lewis acid. So you can use AlCl3 to behave as your Lewis acid to affect a chlorination. So now we've covered bromination with Br2 and FeBr3, or AlBr3, either one works. And now we've covered chlorination with chlorine and AlCl3. Now it says here that fluorination and iodination don't work very well. The reason why is because fluorination is too violent to be practical, and iodination is generally too slow, but generally doesn't mean all the time. And it's very, very rare that I refer to a very specific question in the textbook. So there are other ways of doing both of these. I'll put here, there are other ways. Okay, and I want everybody who's hearing the sound of my voice to look at, on your own time, to look at question 18.1 in the textbook, where it covers a way that you can do an iodination, where you take a benzene ring and you treat it with iodine in the presence of copper 2 chloride, and that will affect an iodination reaction. And I think that there's a question in the homework about this specific question. Somebody asked me in the chat, can you use iron for chlorination too, or just aluminum? You could use iron for chlorination as well. Absolutely, you could. Okay, it just has to be a Lewis acid, an electron acceptor. All right. So again, if we're using aluminum trichloride and doing the chlorination, remember I said that the mechanism was the same? Well, you can see that it's virtually identical. The only difference is that you would replace the aluminum with an iron. That's it. The exact same mechanism, and now you're replacing the bromine with a chlorine. Other than that, it's the exact same mechanism that you saw right here. And so I want you to know the mechanism for bromination, and I want you to know the mechanism for chlorination. I want you to know both of these mechanisms, frontwards and backwards. They're very, very important mechanisms. All right, so it says here, students will sometimes ask me, do you have a summary of this? Okay, well, here's a little summary. It says all electrophilic aromatic reactions discussed in this chapter, they're always going to follow this same mechanism over and over and over. You're always going to have the same old sigma complex. So what's going to happen is the aromatic ring is going to behave as a nucleophile. It's going to react with your very powerful electrophile. You form the sigma complex, and then there's a proton transfer to restore aromaticity at the end. Same old mechanism over and over and over. So if we go, and I shouldn't do this because I'm going to lose track here, but if we go down here to our, what did you call it? The wheel, or I called it the wheel of reactions. We've covered this reaction and this reaction. Okay, so now we're going to move on to another reaction, which is the sulfonation reaction, which I think is somewhere around here. Please, Lord, there we go. Close enough. Okay, so 18.3, we cover a sulfonation. So we're adding an SO3H group to our molecule. And as I told you, this is a new functional group for you. This is called a sulfonic acid. So how do you make a sulfonic acid? Well, and if you're wondering, well, what's the utility of this aryl bromide and this aryl chloride and this aryl sulfonic acid? Don't worry, we're going to get there. We're going to get into that in all kinds of dirty detail. But how do you make a sulfonic acid? It says you use sulfur trioxide, so SO3, this is sulfur trioxide, as your electrophile. And you use sulfuric acid as your acid catalyst. So if you're wondering, like, where do I get sulfuric acid and sulfur trioxide gas? We actually have a name for this. When you combine these two, we call it fuming sulfuric acid. So trust me, there's a difference between sulfuric acid and fuming sulfuric acid, because fuming sulfuric acid contains sulfur trioxide. If you think about the Lewis structure of SO3, we've got a dipole going this way, and this way. So you can imagine that sulfur is super duper electrophilic. So that means if you put this thing in the presence of an aromatic ring, okay, this is going to want to do a nucleophilic attack like crazy on this thing. It even says here in my notes, SO3 is a potent electrophile. Not only is there a dipole, but if you think about the pi bonds, so you notice that I've drawn the Lewis structure here with 3 pi bonds in it. Those pi bonds are really crappy. The orbital overlap is super inefficient because the p orbital coming on or from the sulfur, this is a 3p orbital, and this one on the oxygen is a 2p. And since they have such a big difference in size, they don't overlap very well. And so that's another reason why this sulfur is really delta positive. Okay, it's a really powerful electrophile. So what's the mechanism? Same thing over again. Nucleophilic attack on your powerful electrophile. You make the sigma complex. And then in the last step, water acts as your base to do a proton transfer, okay, to restore the aromatic ring. And then you do another proton transfer to make the sulfonic acid. and that's it. Same old mechanism, just maybe a couple of nuances here because you're in water. But other than that, it's the same old thing again. Now, if I brought up, okay, well, what's the synthetic utility of making a sulfonic acid? If you go back to the alcohols chapter, I taught you about a protecting group, right? We use the TMS, the trimethylsilyl ether, as a protecting group. Well, in this chapter, I'm going to teach you how to use a sulfonic acid, not as a protecting group, but as what we call a blocking group, So we have to be able to remove our blocking group and get a load of this, okay? Sulfonation is sensitive to reagent concentration. And so if you take the benzene molecule and you treat it with concentrated fuming sulfuric acid, you make the sulfonic acid, but you can knock the sulfonic acid off by just treating it with a little bit of dilute sulfuric acid. And if you're wondering why would that be, there's a very good answer to that question, and it's actually covered in the textbook. There, yeah, exactly. Somebody says sulfuric acid is a crazy reagent. It can do all kinds of cool stuff. Well, Mary, that's a good comment. And all mechanisms are reversible, right? There's something called the principle of microscopic reversibility that states that any mechanism is technically reversible, and this mechanism is reversible. And so it's just based on equilibrium, right? You have more water in here, so it would drive the equilibrium towards the aromatic, just towards benzene. Anyhow, there's a little question, like I said in the book, where it actually makes you or asks you to draw this mechanism just so you can see that it's just the exact same reaction, but in reverse. It's just based on Le Chatelier's principle, really. Okay, so now if we go down here, we go, where was it? Here. So now we've covered bromination, chlorination, and sulfonation. And so next we're going to look at reaction 3, which is nitration. And maybe after that, we'll think about calling it a day. We'll see here, see how we're feeling. So the next reaction is nitration. And for nitration, you actually take a mixture of concentrated acids. Wow, this is pretty cool. This is something that we do in the lab sometimes in Chemistry 3111. If you look in the Schaafstal textbook, this is experiment 12.2a, I think is what it is, okay? And what happens here is that the nitric acid actually gets protonated by sulfuric acid. And if you're going, well, they're both strong acids, like how would one protonate another? It'd be a good question. And the reason why it can happen is because the pKa of nitric acid is negative 1.4, but the pKa of sulfuric acid, if you remember, is negative 9. And so that means that sulfuric acid is 10 million times more acidic. So this is 10 million times more acidic than HNO3. Okay, that's a lot. Okay, and so that means that the sulfuric acid can transfer a proton onto the nitric acid and make what's called a nitronium ion. Okay, the nitronium ion. You've got to be able to draw the nitronium ion, which looks a little something like this. Okay, so you get a positive charge here, so you can imagine that's a very powerful electrophile. Okay, here's the believed mechanism of the protonation of nitric acid to make the nitronium ion. So sulfuric acid transfers a proton onto your nitric acid. You lose water as a leaving group, and you make your nitronium ion. And it says here, the nitronium ion is highly electrophilic. So what does that mean? It means if you put the nitronium ion in the presence of an aromatic ring, okay, this thing is so positively charged, that nitrogen, that this aromatic ring is going to be like, hello, okay, it's going to attack it as a nucleophile. Okay, so that would be the first step of the nucleophilic, of the substitution reaction, or the substitution mechanism, which is shown here. So step 1 is the nucleophilic attack. What do we get? A sigma complex. And then in the last step, water comes in, right? Because we're in aqueous acids. It acts as a base, does a proton transfer, and you restore the aromatic ring. And there you go, my friends. Now you've done a nitration. And if you're wondering, well, what the heck would I do with the nitro group once it's installed? I don't remember you mentioning nitro groups a whole lot as being that interesting, So Yes, absolutely. Right. Remember, Audrey, I said the electrophilic aromatic substitution mechanisms. If we go back here, okay, so if we go all the way back here, right, any mechanism, where was the first one? Okay, this is electrophilic aromatic substitution. This one here, bromination. This one here, it's the same thing, electrophilic aromatic substitution, just chlorination. Then this is the generic electrophilic aromatic substitution. Then if we go for sulfonation, again, it's electrophilic aromatic substitution, same mechanism, just a little nuance. Then we go to this one here, nitration, it's electrophilic aromatic substitution, same old mechanism. Nucleophilic attack, sigma complex, proton transfer, done. Then we go here, and that brings us to what would you do with a nitro group? Well, you can reduce a nitro group to an amine, right? And then you make an aniline derivative, or you can make aniline. So this is aniline, right? And that's an amine, and you can do all kinds of stuff with that. So how do you reduce a nitro group? There's a couple of ways to do it, but it says here that one of the best ways to do it is to use iron or zinc and hydrochloric acid. And what this does, step one actually makes the anilinium ion. It actually makes this here, NH3 plus. This is called anilinium. Okay, so anilinium ion, it's got a positive charge. It's a cation, obviously. And so you need sodium hydroxide in the second step to remove the proton from the anilinium to restore it to aniline. And so it says combining these reactions gives us a way to install an amino group on an aromatic ring. Step one, do the nitration. Step two, do the reduction to the anilinium. And step three, convert the anilinium into the free base by removing a proton, just doing a simple proton transfer. And there you have it, my friends. That brings us to the next section, which is Friedel-Crafts alkylation. If we go all the way back, all the way down here, now we've covered halogenation, sulfonation, nitration, and this reduction. So now we're going to get into this reaction, which is Friedel-Crafts alkylation.